Okay, so hello everyone, am I audible? Okay, so hope am I audible? So I'm Subrata from IIT Campus. So I'm one of the TA for the thermal physics course that is taken by Professor Nirmala Banerjee. This course is already has been running for the past 12 weeks. Okay, at NPTEL. So today this sessions will be my final one. So in this sessions, okay, I'll solve assignment 12 problems, right? And if time permits, okay, I'll also touch some extra problems, okay, that is related to the uh, black body radiations, okay, and also second law of thermodynamics, right? So if you have any questions, you can ask me, or you can also write up in the chat. So any questions from the previous week or week content? Okay, so I'll share my screen. So yeah, my screen is visible, right? Okay, so it seems there is no question, so I'll then start to solve assignment 12 problems. So in the first problems, so I'll go on by one, and in the meantime, if you have any questions, please, okay, raise your questions. Okay, yeah, okay, unmute yourselves and ask the question directly. Okay, and don't hesitate to ask any questions. Okay, so okay, so in the problem on, okay, so in the problem on, so a wire of length 1 meter and radius 1 millimeter is heated via electric current to produce 1 kilowatt of radiant power, right? So treating the wire as a perfect black body and ignoring any end effect, okay, calculate, yes, so calculate the temperatures of the wire given the Stefan constant is this. Okay, so length and the radius is given, right? So that means it's basically cylindrical type wire, okay, and heated by electric current, okay, and the radiant power is produced 1 kilowatt, right? So these data are given. Okay, so your length L is 1 meter and radius R is 1 millimeter. So first convert to SI units. Okay, so 10 to the power minus 3 meter, right? And the power P is 1 kilowatt, right? So it's the radiant power, right? So this data are given, and also the values of Stefan constants are given. So 5.67 times 10 to the power minus 8 watt per meter square per Kelvin to the power 4, right? Yes, you have to calculate the temperature of the wire, right? And you have to assume that your wire is a perfect black body, right? So for perfect black body, then your power emission, the radiant power, is equals to the electric power, right? So what is the formula for the power then? So it's very simple. So if we use the formula, let's first copy this data. Okay, so it's the problem number 1. Okay, so this is the these are the data, okay, that is given, the values P, okay, radiant power. So now we know that if the wire is a perfect black body, so the radiant power, right, so radiant power P is basically, what is the formula of the radiant power? So it's proportional to T to the power 4, right? So that is important. So, and the constant, basically the Stefan Boltzmann constant, right? So sigma times area, so A is the area of the wire, okay, times T to the power 4, right? So that is the radiant power. Is there any, okay, so that is the radiant power, okay. Okay, wait. Okay, so it's audible, right? Okay, so then the power is basically sigma 80 to the power 4. So now we go back to the questions again, right? So in the questions you have to compute the temperature of the wire, okay, and the power is given 1 kilowatt. So all the data are given. So now we have to calculate the area. So your area A equals to, is a cylindrical wire, so 2 pi times radius r times length L, right? So r is given 1 millimeter, so it's 10 to the power minus 3. So 2 pi times 10 to the power minus 3 meter times 1 meter, right? So it's basically meter square. So all are in the SI units. So then the power is 1 kilowatt, so it's basically 1000 watt, right? So it's equals to sigma is 5.67 times 10 to the power minus 8, right? So this is watt per meter square per Kelvin, Kelvin to the power 4, times area. So area is this 2 pi times 10 to the power minus 3, right, times t to the power 4, right? So then the t to the power 4, T equals to the temperatures equals to 1000 over 5.67 times 10 to the power minus 8 times 2 pi, right, times 10 to the power minus 3, right, to the power 1 over 4, right? Okay, so then use your calculator to calculate this. Okay, so the results is 1294 the Kelvin, okay, so 1294 Kelvin. So please cross check this answer, okay. So use your calculator, okay, calculate this. This is 1294 Kelvin, okay. So okay, so let's check the option. 1294, yes, so the option B is correct, okay. Yeah, any question? So when the wire the length and the radius of the wire is given, okay, so then you can easy to calculate the area, okay, and once you know the area you can calculate the power, okay, because Stefan Boltzmann constants already given, okay. And we also assume that your wire is a perfect black body, okay, so then the power is exactly same as for the perfect black body radiations. Okay, so it's sigma T to the power 4 times A. Okay, so Stephen Boltzmann constants. Okay, it's true for the perfect black body. And calculate the temperatures of the wire. So it's very simple. Okay, right. So once you know this too, you can calculate T to the power 4. This is so we follow the steps. Okay. So now the data is changed, so you can easy to calculate for any other values of, or sometimes the temperature is given, you have to calculate the power. Okay, radiant power. Okay, okay, so then I will move to the next one, right? So in the next question, so cavity radiator, okay, has its maximum spectral radiance at a wavelength of 1 micrometer, right, in the infrared region of the spectrum. So wavelength 1 micrometer. So but this wavelength where the spectral radiance maximum, right? So basically your spectral radiance means that u lambda. Okay, so energy, spectral energy density. Okay, so u lambda is maximum at lambda max is 1 micrometer, so basically 10 to the power minus 6 meter, right? So this u lambda is basically spectral radiance, spectral energy density, right? So spectral energy density. Okay, and the temperature of the body is now increased so that the radiant intensity of the body is doubled, right? So first you have to calculate the temperature of the body. Okay, then the temperature of the body is increased so that the radiant intensity of the body doubled. Now the temperature will be, okay. So first you calculate T1, okay, when the lambda max is 10 to the power minus 6 meter. Okay, then you increase the radiant intensity, okay, and how the temperature changes. Okay, and you have to calculate the final temperature, right? First you have to calculate T1, okay, from this data. Okay, so how to calculate T1? Okay, so how to calculate this? Because if you know the Wien's law, right? So it's problem number 2. Right, so wind displacement, so it's basically lambda max. So lambda max, the maximum wavelength times temperature equals to constant. Okay, and the values of the constants is basically Wien's constant is 2.897 millimeter times Kelvin, right? So millimeter times Kelvin. Okay, so now the lambda max is given. Okay, so lambda max is basically the maximum wavelength. So the values of the wavelength where the u lambda is maximum, right? So lambda max is given. So lambda max is 1 micrometer, right? So it's 10 to the power minus 6 meter. So then that values of T is basically 2.897 into 10 to the power minus 3, which converted to meter. okay, SI units divided over 10 to the power minus 6, right? So then the values of T is Kelvin, right? So it's 2897 Kelvin, right? Okay. So once you know the T, now the second part. So first part is done, right? So now the second part is that, yeah, so now the temperature of the body is increased so that the radiant intensity of the body is doubled. Okay, so radiant intensity doubled means the power double, right? And we know how power is related to temperatures, right? Or the intensity is related to temperature, right? So it's basically proportional to T to the power 4, right? So your radiant intensity, let's say I. So second part is that, so radiant intensity, right, I is proportional to T to the power 4, right? So I1 over I2 is basically T1 over T2 to the power 4, right? Now if we increase the temperature, okay, such that your radiant intensity is doubled, right? So I2 becomes 2I1, then you have to calculate T2, right? But the T1 is this, so let's say the T1 is 2897 Kelvin, right? So put this value here. So your I2 is 2I1, so 1 over 2 equals to T1 over T2 to the power 4, right? So T2 is basically T1 times 1 over 2, sorry, T1 times 2 to the power 1 over 4, right? And this 2 to the power 1 over 4, right, so is greater than 1, right? So the value is basically 2897 times 2 to the power 1 over 4, so 3445 Kelvin. So please cross check this answer. Okay, okay, so let's check the options. Okay, so 3445 Kelvin, right? Yeah, so the option D is correct. Okay? Yeah, any further question or any doubts? So these questions has two part. Okay, so in the first part you have to calculate the temperatures, okay, from the lambda max. So from this you use Vin displacement law, right? Because the maximum spectral radiance at wavelength is given. So once you know the temperatures, okay, now if you increase the temperature, in the second part, now if you increase the temperature, okay, your radiant intensity is doubled, right? So you have to know that how radiant intensity, okay, it depends on the temperature. Once you know this, okay, you can calculate the final temperatures, okay, when the intensity is doubled, right? Okay, so this is your A and this is your B. Okay, two parts. Okay, so then I will move to the third question. So in this problem, okay, any question? Okay, so in this problem, so the pressure inside the sun, okay, it's estimated to be the order of 400 million atmospheres, So the pressure inside the sun. Estimate the temperature corresponding to such a pressure, assuming it results from the radiation. Right. So the energy density, how the pressure related to the energy density, right? So okay, so if you know the equations of state of a black body radiation, okay. So I've discussed in the previous class, right? So in the static class, I discussed that how the pressure related to the energy density or the temperatures, right? For a black body radiations. And what is the equations of state of a black body? So if you uh, know the equations of state of the black body, so this is basically how pressure related to other variables, right? So you can also write the equations of state in terms of energy density. So okay, so problem number 3. So the equations of state, so the energy density U, equation of state. Okay, so this is basically the energy density U and P, energy density U and pressure P, so this pressure is small p, okay, and the power is capital P. Okay. So the small p is pressure, okay, and energy density U, okay. So pressure of radiation is related by so it's basically small p equals to U over 3, right? So 1/3 U, right? And you know what is the values of U, right? So is U basically, sorry, yeah, 4 sigma t to the power 4 over 3, right? So 3c, 4 sigma t to the power 4 over 3c, right? So this is the U, the energy density, okay, for a black body radiation. So then the pressure P equals to, no, this is basically 4 sigma t to the power 4 over c U, and P is basically 4 over 3 sigma t to the power 4 over c. Okay, this is the C, sorry, this is the P. Okay. Right. So this is U, basically energy density for the radiation, okay, and this is basically your equations of states. So P equals to U over 3, and that tells you that how energy density and pressure are related, okay, of the radiations. So from this you have to calculate the T, temperature, right? So temperature is basically 3Cp small p over 4 sigma, right, to the power 1 over 4. So now you go back to the problem. Yeah, so in the problem the pressure is given, so pressure small p is 400 million 10 to the power 6 atmosphere, right? And yes, so this is the pressure, and estimate the temperature corresponding to such a pressure, assuming the result from the radiations, okay. So if from the radiation you consider the black body radiations, okay, and your energy density, uh, yes, so your energy density is U lambda to the from this, okay, right, and the equations of state is this. So you have to calculate the temperatures, right? So this is the temperatures, and where the pressure P is given, okay. This is basically, now we have to convert in SI units, so Pascal. So 400 times 10 to the power 6 times 1.013 times 10 to the power 5, right? So that is basically a Pascal or Newton per meter, right? So it's Pascal. Okay, sorry, so 1.013 Pascal, and that is basically Newton per meter. Newton per meter, yeah. So this is basically in the SI unit space, right? Newton per meter square. Okay, force per area, so Newton per meter square. Okay, right. So this thing you have to check. Okay, so then you just put this value here. So your T is equals to, so your T is equals to, then 3 times, what is the values of C in SI unit? So it's 3 times 10 to the power 8, right? And then the values of the pressure is 400, or 4 times 10 to the power 8 times 1.013 times 10 to the power 5 Newton per meter square, all in the SI units, divided by 4 sigma. 4 times your values of sigma is yeah, so your values of sigma is the Stefan's constant, so it's 5.67 times 10 to the power minus 8, right? 1 over 4, right? If you compute this, okay, so use your calculator, so the result is 2 times 10 to the power 7 Kelvin. Yeah, so this is the values of temperatures of the temperatures of the sun. Okay, so 2 times 10 to the power 7 Kelvin. Okay, so let's check the option. Yes, so 2 times 10 to the power 7, option A is correct. Okay, right? Any question? So this is in the ATM, so you have to convert basically in the SI unit, right? So times 1.013 10 to the power 5 Newton per meter square. So choose one unit consistence throughout the problems. Okay, so I choose SI unit, so everything's okay. Convert to the SI unit, right? This is a very simple problem. Okay, and so you first yeah, so you first write down the formula for the energy density. Okay, because you know that it is for the radiation, so you know the energy density for the radiation. So, and then how the pressure related to energy density, you have to use the equations of states. Okay, so these two, and just algebraic simplifications. Okay, have to calculate the temperature. So, okay, so yeah, any question further? Okay, so I will move to the next one. So in the next problem, Okay, so in the next problem, an iron ball having a surface area 100 centimeter square, okay, and temperature is 527, okay, 527 degrees centigrade, is placed in an enclosure of 27 degrees centigrade. So basically your iron ball that enclosure with another surface of temperature is 27 degrees centigrade, right? So your surface temperature is 27 degrees centigrade and your iron ball, the core temperature is 527 degrees centigrade, okay, 527 degrees centigrade. So basically your T1, so this is basically your core iron ball temperatures, okay. So this is iron ball temperature, right? It's the core iron ball temperature, okay, and this T1 is 527 degrees centigrade, so you convert it to Kelvin, so it's 800, right, 273, so 800 Kelvin, right? And your surface temperature, so this is basically surface temperature, it's T2, right? Okay, so it's basically enclosure temperatures, okay, surface temperatures, and this T2 is 27 degrees centigrade, so it's 300 Kelvin, right? Okay, and the surface area is basically 100 centimeter square, okay. So you have to convert into the SI units, okay, because I will use SI unit, okay. So your area is 100 centimeter square and the emissivity, so emissivity of iron beam is 0.3. At what rate the heat is being lost by radiation by the ball, okay, so by the core, okay. And also the emissivity of iron beam is given 0.3, right? So the values of E is 0.3, the emissivity, okay. And yeah, so the area A is basically 100 centimeter square, so 100 times 10 to the power minus 4 meter square, right? So I converted to SI unit, okay. So yes, copy this thing, per 4, right? So just copy this, okay. So you have to calculate the heat, right? So you have to calculate yeah, we have to calculate the rate is heat being lost by radiation by the ball, okay. So energy loss per unit time, so that is basically rate, okay, by the ball, okay. So you have to compute the energy loss, so energy loss by the energy loss per unit time, okay, due to radiations, okay, or by the ball, so by the iron ball is, so this energy loss per unit time is basically your heat loss due to the rate of heat loss, okay, due to radiations, okay. This basically rate of heat loss or heat lost, okay, due to radiation, okay. So it's the same thing, okay. So this is basically Q equals to the energy loss or heat loss, okay. So this Q is basically A, the area times sigma times T to the power 4. So now we have two temperatures, one is the core temperature and the surface temperature. So T1 minus T2, so core minus surface, and T1 to the power 4 time minus T to the power 4 times the emissivity E, okay. because the emissivity of the iron ball is given, okay, 0.3, it's not 1, okay, right. So okay, so then we put everything in the SI unit. So the values of Q then is basically A is area, so 100 times 10 to the power minus 4, right, and your sigma value is in SI unit 5.67 times 10 to the power minus 8, okay, watt per meter square per Kelvin to the power 4, right. So yes, and then the T1, so T1 is 800, so 800 to the power 4 minus 300 to the power 4, right, times emissivity 0.3, okay. So ultimate unit is basically a joule per second, okay. So you have to convert yes, so per unit time, so joule per second, okay. So okay, so after simplifying this, so it's basically 68.295 joule per second. So check this, okay. So use your calculator, okay, to calculate this. So you find the 68.295 joule per second. Yeah, any question? Okay, so let's first check the options, okay. So 68.295, 68 point, okay, so the answer given in calorie per second, right, but you compute, so there is a very close to this 68.3, but this is not correct, right, because the unit is calorie per second, right, but you just compute, okay, so you just compute in joule per second, right. So you converted this, so 1 calorie is basically 4.2 joule, right. So you have to divide it by 4.2, so 68.295 over 4.2 calorie per second, right. So then your answer is Q equals to 16.26 calorie per second. Now you check the options. So 16.26, yeah, it's very close to B. So very close here. So option A is the number, right. So 68.3 is very close to 68.295, but the unit is calorie per second, okay. But you calculate it in joule per second, right. So 60.2 calorie per second. So option B is correct, okay. Yeah, any question, any doubts? Yeah, so basically watt is joule per second, okay. So 1 watt is 1 joule per second, okay. Because the, so here it is basically watt, right. So 5.67 into 10 to the power 8, so the unit is watt per meter square per Kelvin to the power 4, right, and this is meter square and this is Kelvin to the power 4, so this is basically watt, right. So watt are left, so meter square Kelvin, Kelvin to the power 4, Kelvin to the power 4 cancel, so only left with watt, right. So this watt is basically joule per second, okay. So all right, okay, so then I'll move to the next one. So in the next problem, yes, so the problem number 5, So a spherical black body with radius 12 centimeter radiates 450 watt power, okay, at 500 Kelvin. If the radius were half and temperature doubled, the power radiated in watt will be, okay. So the spherical black body with radius is given, right? So the black body is basically a sphere, okay, is spherical type, okay, and your radius r is 12 centimeter, okay. So you have to calculate area. So this, since it is a sphere, so 4 pi r square, right? The area is a spherical black body, and yeah, so and radiate power, let's say P1, okay, 450 watt, okay, at T1 is 500 Kelvin, right? If the radius were halved, okay, so let's say this is in R1, area A1, and this is your R1. So now your radius R2 is basically half of this, so 6 centimeter, right? Then the power radiate in watt will be, so calculate P2, okay, you have to calculate P2, right? Okay, so then how to calculate? So this is very easy, right? So the radius is given of the black body, and the also power and the temperature, right? And if the radius were halved and the temperature double, okay, also T2 is basically 2T1, okay. So radius R2 is basically R1 over 2, okay, and you have to calculate P2 when the T2 is also 2T1, right? So you have to know how radiate power, okay, radiant power is depends on area and temperature, right? Because only the two variables are changes, okay, radius, that means area, and the temperatures, right? So if you know this, you can quickly solve this problem, okay. So it's 5, right? So the radiant power, so capital P, right, is basically area times sigma times 10 to the power 4, right, for perfect black body, right? So then P1 over P2, so sigma is a constant, okay, Stephen's Boltzmann constant, so it's constants for different values of radius and temperatures, right? So it's a universal constant. So your area A is basically 4 pi r square, right? So that means P1 over P2 is basically R1 square over R2 square times T1 to the power 4 over T to the power 4, right? This 4 pi is also constant, okay. So now in the problem, it's R2 is basically R1 over 2 and T2 is 2T1, right? So R1, sorry, R2, so R1 square and R2 is basically R1 square over 4, right, times T2 is 2T1, so T1 to the power 4, right, 16, so 2 to the power 4 is 16, so 16 T1 to the power 4, right? So it's basically 1 over 4, so I left with 1 over 4, right? So hence P2 is basically 4 times P1, right? So P2 is 4 times P1. Okay. So therefore 4 times your P1 is given 450 watt, right? So 450, right? So basically 4 times 5 is 20, so it's 1800. Okay. So 1800 watt. So this is your radiant power. Okay, right? Since the temperature, we do not need the absolute values of the temperature, so because temperature is cancelled. We also do not need the absolute values of the radius. Okay. And it depends on the power, right? Okay, so let's check the option. So 18 watt. Okay. Sorry, 1800 watt. Yeah, so the radiant power. So basically the units is watt. So 1800 watt. Okay. So option D is correct. Yeah. Any question? Okay, so is there any question? Okay, so if not, then I will move to the next one, right? So in the next problem, so calculate the pressure exerted by sunlight on the Earth's surface, given that the solar constant is this. Okay. Okay, so the intensity of the radiation is given, right? So I, the intensity of the radiation. So intensity of radiation I it's 8.148, so joule per centimeter square per minute, right? So I have to convert first in SI unit, so joule per meter square. So then divided by 10 to the power minus 4, right, times 60, converted to second, right? So joule per meter square per second. So that means it's basically watt per meter square, right? So basically 8.148 times 10 to the power 4 over 60, okay, watt per second. Okay, so watt basically joule per second, so watt per meter, right? So now we have to calculate the pressure of the radiation, right? So how pressure related to intensity? So pressure of the radiation then given by pressure of the radiation is given by P equals to I over C. So intensity over the speed of light, right? So it's basically 8.148 times 10 to the power 4 over 60 times 3 times 10 to the power 8, right? So 10 to the power 8 meter per second, so it's basically watt, right? Or the unit is basically Newton per meter square, right? So this is basically a pressure, right? Okay, in SI unit, so the value is then 4.52. So once you compute this, okay, so your pressure P is 4.52 times 10 to the power minus 6 Newton per meter square. Okay, so please cross check this. Okay, so let's check the options. 4.52 10 to the power minus 6 Newton per meter square, so that means it's Pascal, right? So 1 Newton per meter square, basically 1 Pascal. So it's option C, right? 4.5 is very close to this. So yeah, so up to one significant digit, okay, it's 4.5. Okay, yeah, so 4.5 into 10 to the power minus 6. So the two significant digits. Okay, yeah, any question? Okay, so then I'll move to the next one. So in the next problem, the absorptive power of a black body at red and blue light are respectively given as A rate this, so absorptive power, okay, so A rate is 300 watt per meter square, and absorptive power for blue light, A blue, right, 400 watt per meter square. Find the ratio of emissive power at red and blue light. Okay, so ratio of emissive power, right? So for Kirchhoff law, right, know that the A over E is basically constant, right? So if you know that Kirchhoff law, so from Kirchhoff laws, law, basically absorptive power over emissive. Okay, so E is emissive and A is absorptive. Okay, absorptive power, so is basically constant. Okay, so therefore A rate, I mean each proportion is related to A over E is basically related to your E over A. E over A is related to C over 4. So let's say E lambda and A lambda for a wavelength lambda. Okay, C over 4 U lambda. Okay, so it depends on the energy density, spectral energy density at this wavelength lambda, right? Okay, so therefore this E lambda over, so E blue, okay, so this, okay, so this is problem number 7. Okay, so this came from basically so if you know that in thermal equilibrium, so in thermal equilibrium, right? So in thermal equilibrium, your P, the power, okay, radiant power for absorptions equals to P emission, right? So therefore the absorptions power is 1 over 4 U lambda at a wavelength lambda d lambda times speed of light c, and emission power is basically E lambda, the emissivity rate, okay, times d lambda, right? So this E lambda over, and this times the absorption coefficient A lambda. Okay, so therefore E lambda over A lambda basically C over 4, right? So from this you can easily verify this. Okay, so this is basically a Kirchhoff law. Okay, so then your E rate over E blue, right, equals to A rate over A blue, right? Right. So which is equals to, so A rate is 300 and B rate, A blue is 400, right? So this one basically 3 over 4. Okay. So E rate over E blue is 3 over 4. Okay. So in the problem, you have to calculate the find the ratio of emissive power at red light and blue light, right? So it's 3 over 4. So it's proportional to your emissive power. Okay. So absorptive power is proportional to emissive power. Okay. Yeah, any question? So if you go into that more details, so basically your E lambda over A lambda, right? So aside, Okay, so E lambda over A lambda is basically is a functions of is a universal function of lambda nt, because u lambda is a functions of lambda nt, right, wavelength and temperature. So it is a universal functions of lambda, wavelength and temperature, right, t, right. So if we fix lambda and t, so if we fix lambda, wavelength and temperature, so this implies that your E lambda is proportional to A lambda, right. So emissive power is proportional to absorptive power, okay, at a given wavelength, because lambda and t fixed. Okay. So a perfect black body is an object. So a perfect black body is an object for which alpha lambda equals to 1 for all lambda. Okay. So this is basically a perfect black body. So this is basically a gas of photon. So black body means that the gas of photon, okay, content in a black body cavity. Okay. So gas of photon, okay, content in, so content in the black body cavity, black body cavity. So this is known as the black body radiations. So black body radiations, okay. So in short, BBR, okay. So black body radiations. So basically gas of photon content in the black body cavity, and the radiations from this, okay, is a black body radiation. So, okay, and so A lambda, sorry, so this is A lambda. Okay. So perfect black body where the absorptions power is equals to 1, okay, rate equals to 1, so for all lambda, so that is about the perfect black. Okay. So okay, so then okay, so if there any question. Okay, so okay, so then I'll move to the next one. So the problem number 8. So close to absolute zero temperature, difference between specific heat goes to, yeah. So in the previous class we discussed that what is the uh, behavior of specific heat, okay, when the temperatures on the absolute zero, okay, when the temperature goes to absolute zero. So basically the Thaler thermodynamics tells you that the Cp and Cv all are goes to 0 as T goes to 0, right? But you can also show that the difference between these two, Cp minus Cv, right, difference of the specific heats, is basically is related is T V, okay, and then alpha the expansivity, okay, and del P over del T at constant, right? Since T goes to 0, so at absolute 0 temperature, so T is 0. So if T is 0, then the difference Cp minus Cv is also 0, right? Because if you use these relations, okay, and it can be shown from the second law of thermodynamics, right? So Cp minus Cv, right? So go back to the previous classes, okay, and recall your class notes, okay. So this thing is derived, okay. Cp minus Cv is related to the temperatures, okay. And yeah, so if T equals to 0, then this difference is also 0. So the option C is correct, right? Yeah, any doubts? Okay, so if not, then I'll move to the next one. So in the problem number 9, so calculate the ratio of specific heat at constant volume and absolute entropy for a cavity, okay, maintained at 1000 kelvins. Calculate the ratio of specific heat at constant volume and at constant entropy, okay, and absolute entropy, sorry, and absolute entropy for a cavity. So this basically is maintained at temperatures 1000 Kelvin, right? So your temperature T is 1000 kelvins, and you have to compute the ratio of Cv over S, right? How to compute this? So in the previous class we have discussed this, right? How so what is the Cv for a black body radiation? So for a black body radiations, so you have to compute this. So 8. So for a black body radiation, right? Free energy F is minus 4 sigma over 3c, right, t to the power 4, right? This is the free energy, right? And your Cv is basically 16 sigma Vt cube over, sorry, I think there is also V, so Vt to the power 4 or cube, okay, so let me check what is the free energy for black body radiations. Yes, so V to the power 4, right? So times the volume V, okay, and minus 3 sigma of course. Yeah, so that this is correct, okay. And Cv is basically power 7 to T cube, okay. There's on more derivatives, right, with respect to temperature. So this is basically 16 sigma Vt cube over C, okay, and the entropy is basically 16 sigma over 3c, again the same dependence Vt cube, okay. This is basically also related to one more derivative of free energy with respect to temperatures, okay. So first derivative, so that's why T cube, okay. So all are same temperature dependence, okay. So once we take the ratio Cv over S, so the temperature dependence actually cancel out, so you do not need the informations, okay, at what is the temperature, okay. So because Vt cube cancel, so only left with 16 sigma over C over 16 sigma over 3C is basically 3. Okay, so Cv over S is 3. Okay, for black body radius. Sorry. So yes, so calculate the ratio of specific constants. So cavity is basically black body radiation. So cavity is a black body. Okay, so because cavity is a black body. Okay, and the cavity radiation is a black body radiation. Okay. Okay, any question? Okay, no question. Okay, it seems that there is no question, so then I will move to the next one. So cavity with volume 5 liter, okay, is maintained at 4000 Kelvin. For the system, calculate enthalpy. Okay, so volume is given 5 liter, right? So V is 5 liter. Okay, so first convert it to meter cube. Okay, because I use SI units. So 1 liter is equals to 10 to the power minus 3 meter cube, right? So 5 liter is 5 times 10 to the power minus 3 meter cube, and your temperature T is 4000 Kelvin. Calculate the enthalpy. So H basically E plus PV, right? So E is the energy, internal energy, right? And we know that energy is basically minus 3F, okay, free energy. So this is basically minus 3 times minus 4 over 3 sigma C Vt to the power 4. So therefore it's 12 sigma over 3C Vt to the power 4, and the pressure P is basically 4 sigma over 3C Vt to the power 4, sorry, T to the power 4. So therefore H is equals to 12 sigma over 3C Vt to the power 4 plus 4 sigma over 3C again Vt to the power 4, right? Because T to the power 4 times V, okay, PV. So therefore 16 sigma over 3C V to the power 4. So any question up to this point, okay? So up to this point, no question, right? Yeah, so the next part is that you just plug put the values, okay, because we know the V and T, right? So H, then 16 times sigma, right, 5.67 times 10 to the power minus 8, so in SI unit, right? So watt per meter square per Kelvin to the power 4, and your volume V is 5 liters, so 5 times 10 to the power minus 3 meter cube, right? And then the temperature T, so it's 4000 to the power 4, right, over 3C, right? So 3 times C is 3 times 10 to the power 8, right? Again in the SI units, right? So this becomes 1.29 times 10 to the power minus 3 joule. Okay, so 1.29 times 10 to the power minus 3 joule. This is the enthalpy of. Okay, okay, so let's check the option. So 1.39, so yes, so it's a millijoule, so 1.329, right? So it's basically 1.29 millijoule. Okay, so option C is correct, right? So 1.29 millijoule. Okay, so option C is correct, right? Yeah, so any question, any doubts? So this in this problem, so we first calculate the age. Okay, how age depends on volume temperatures. Okay. So you know that how energy, so in the previous class I derived those things. Okay, so how, so this is basically E equals to minus 3 AF, okay, and then these, okay, and the pressure is P. So this relation, so go back to the previous class. Okay, I discussed those things. Okay. So if we use this formula, okay, we can calculate age, basically E plus PV. This becomes 16 sigma over 3 C V T to the power 4. Now put the values of the constants. Okay, so since there is a time left, so I'll discuss some extra problems. Okay, okay. So let me check. Okay, so let's solve one or two problems. Okay, so in the first problems, so let's consider Earth and Sun. Okay, behaves like a black body. So let's consider Earth and Sun. Okay, behaves as a black bodies. Okay, and the temperature of the Earth's surface temperature of the Earth's surface is maintained by radiations from the sun. Okay, so it's maintained by radiation from the sun. Okay, calculate T Earth over T sun. Okay. So temperature, the ratio of the temperature at Earth, okay, over the temperatures at sun. Okay, so calculate this. Okay, so how to compute, how to calculate this ratio? So we first calculate the power, right? So power emitted from the sun. So first if you calculate the power emitted from the sun. So it's basically PS. What is the power emitted from the sun? Again, sigma T to the power 4 times area, right? So let's consider both are the spherical objects. Okay, so sigma Ts to the power 4 times area, so 4 pi r square. Okay, so this power known at its luminosity, right? So this power basically emitted from the sun is the luminosity, right? And the power incident on the earth is, so power incident on the earth. So power radiated from emitted from the sun, this, and power incident on the earth, okay, is basically luminosity L, right? So this is basically luminosity. Okay, so this power known as, so this is basically luminosity L. Okay, so this L times pi re earth square over 4 pi d square, right? So d is basically the distance between earth and sun. Okay, so where d is basically distance between earth and sun, right? So basically if we draw a picture, so let's think of this way. So this is your sun, your spherical object, let's look like a spherical. Okay, and these things, okay, okay, and this is the your radius. So the distance between earth and sun, so basically if we also draw a earth, right, and your earth radius, right? So this is the re earth radius, and this is the distance between earth to sun is d. Okay, and this is the sun. Okay, right, so this is your sun. Okay, and this is the distance between earth to sun. Okay, d, right? So power incident on the earth is luminosity times pi re square, right? So this is your re, so the area of this circle, okay, it's pi re square. Okay, and we consider a sphere around the sun, okay, with the distance d. Radius is basically distance. Okay, so this is your sphere. Okay, and this is your sun. Okay, right? So now the power emitted from the earth. So the next, power emitted from the earth. So what is the power emitted from the earth? So then again this is a 4 pi re square. So power emitted from the sun is similar to that. Okay, so 4 pi re square times sigma TE to the power 4, right? Okay. So equate the power on the earth's surface. So if we equate the power on the earth's surface, so equate the power, okay, so equate the power on the earth's surface, emitted and incident on the earth, okay. So power incident on the earth this, and power emitted from the earth this. So equate the power on the earth's surface, okay. So we get 4 pi r square sigma times Te to the power 4 times this, okay, is equals to sigma Ts to the power 4 pi r square, right, times pi re square over 4 pi d square, right. So we are left with Te over Ts, then so basically this re cancel, so r square cancel, and then sigma cancel, okay, 4 pi cancel, okay. So you are left with this, so Te over Ts, okay, so the earth temperatures over the sun temperatures, basically square root of Rs over 2D, okay. So this is the results, okay, Rs over 2D. So now let's say given the radius of the sun Rs is 7 times 10 to the power 8 meter, and the distance between earth and sun is 1.5 times 10 to the power 11 meter, okay. And the sun temperature is given 5800 Kelvin, okay. So then we can easily, so given this data, okay, so you can easily compute the Te, the earth temperatures, okay, is basically 280 Kelvin, okay. So please cross check this, okay. So this is the on problems. Yeah, any question from this? So first to calculate the power emitted from the sun, that is basically your luminosity, and from this is basically absorbed in the on the earth. So you calculate the power incident on the earth, okay. Not all the powers are incident on the earth, so there is some fractions of this, okay. So this is the fractions, okay, pi r square over 4 pi d square, okay. And we have to also calculate the power emitted from the earth, and then we equate the both powers, okay, the incident on the earth and emitted from the earth, okay. So these are equals, okay. So we get this, okay. So this is the result. So given this data, we can calculate the earth temperatures easily, okay. Yeah, any question? Okay, so let's do one more problems quickly. So it's Q2. This is basically the problems of solar constants, okay. So the radiation flux, okay. So what is the solar constant? So the solar constant is basically the radiation flux, okay, at the surface of the earth, right? So radiation flux at the surface of the earth, right? So given the solar constant, so given the value of solar constant, is 0.1 watt per centimeter square. The find out the temperature of the sun. Find the temperature of the sun. Temperature of, okay. So find the temperature of the sun. Okay. So how to calculate? So what is the power per unit area? So it's the radiation flux, right? So flux is basically the per unit area, right? So the radiation power per unit area, right? So what is the radiation power per unit area? So radiation power per unit area, right? P equals to sigma Ts to the power 4, right? Is the temperature of the sun, Ts. Okay, and the solar constant is basically the surface of the earth. So radiation flux at the surface of the earth, right? So then sigma Ts to the power 4 times 4 pi Rs square over 4 pi d square, right? This is equals to 0.1. Okay, so d is the distance between earth and sun. Okay, so the d is the distance between earth and sun. Okay, and since it is unit area, so if you multiply it with this flux, okay, with the area, okay, so 4 pi r square times sorry, over 4 pi d square. Okay. So this is basically 0.1. This is basically watt per centimeter square. So given the Rs, basically 7 times 10 to the power 8, so this is given meter, and your diameter d, it's 1.5 times 10 to the power 11 meter. Okay, you can calculate the Ts, the sun temperatures, is around 6 times 10 to the power 3 Kelvin. Okay, so please cross check this. So, right. Okay, so please cross check this, and yeah, any question? So please feel to ask any questions if you have. Right, so this rs is the basically your radius. Okay. Okay, so then okay, so it seems there is no more questions, then I will stop here. Okay, and yeah, so I hope you enjoy these seasons, enjoy this all the seasons. Okay, and you also enjoy the classes. Okay, and I hope you got your doubts clear. Okay, so if you have any questions, since the your NSEM exams are approaching, so as the NSEM exams are approaching, so okay, so you have any questions, so please feel free to reach out over emails. Okay, so my email ID email is